All right, young ones, today I'm going to begin my soiree into copyright infringement. Now, whatever, I'll leave my picture there. My face is all covered up anyways. Hi. Now, I want to make sure to state this beforehand because I'm just helping this with my students. All right, so let's get started. All right, so please remember that paper one is in order of topic. Right, so the only topic I did really out of order was we did a little bit of organic in the beginning of the year. So it follows the sequence of the year. So we start with unit one, which was quantitative chemistry. So number one says, how many moles of FeS2 are required to produce 32 grams of SO2? We're given the relative atomic mass of sulfur and oxygen. So in general, if you're ever given an amount of one substance and asked how much of another substance forms, that is a stoichiometry problem. So we have our coefficients that give us the mole ratio. So if we figure out how many moles of SO2 we've got, if we look here, for every 4 of those used, we make 8 of those, so we'll have double the amount. All right, so first thing we got to do is find out how many moles of SO2 we have, and from then we can figure out how many moles of FeS2 must have reacted. So we have 32 grams. To get the number of moles, we have to divide by the molar mass of SO2. So S is 32, each oxygen is 16, so the molar mass is 64. 32 divided by 64 means we have 0.5 moles of SO2. Well, remember, we're going to have double the number of moles of SO2. That means we'll have 0.25 moles of that form, so the answer is A. All right, number 2 says the volume of a sample of gas was measured at 27 degrees Celsius to be 10 cubic decimeters. What is the temperature when the volume is reduced to 9? All right, so we are changing the volume. We want to know what the temperature is, so that becomes our... I believe this one is Gay-Lussac's law, P1 over T1 equals P2 over T2. Now remember, the T's have to be in Kelvin. Right? So we are given Celsius. To go to Kelvin, we have to add 273, which means our T1 is 300. So now let's just go ahead and plug a chugga and a solva. Pretty simple, really. So P1 is, or I'm doing P's, it should be V's, whatever. So V1 is 10.0 cubic decimeter divided by the T temperature initially, which is 300 Kelvin. And we want to know what is the temperature when the pressure is changed to 9 cubic decimeters. So this will work out to be 2,700 equals 10.0 times our variable, which I called X. I'll just make it bigger. So that means X here will be equal to 270 Kelvin, which in Celsius, we subtract 273, so the temperature is -3. All right, number 3. An antacid tablet containing a half a gram of sodium hydrogen carbonate gives you the molar mass as well as dissolved in water to give a volume of 250 cubic centimeters. What is the concentration in moles of HCO3- in this solution? So remember, if we want the concentration of the hydrogen carbonate ion, I need the number of moles of that ion divided by the volume of the solution we make. So moles is mass over molar mass, so that'll be 0.5 over the molar mass, which is 84, right? And we want to, this is moles, we want to divide that by the volume in cubic decimeters, that's cubic centimeters, so divided by 0.250. So the one I see that looks like that is choice B. D looks similar, but it's by cubic centimeters and blah, blah, blah. All right, number 4, which statements are correct for the emission spectrum of hydrogen? Well, number 1 says the lines converge at higher frequency. Well, they converge at higher energy, and higher energy equals higher frequency, so yes. Electron transitions to n equals 2 are responsible for the lines in the visible region. Indeed, transitions to n equals 3 give us the infrared, and transitions to n equals 1 give us the ultraviolet. And lines are produced when electrons move from lower to higher. No, that represents the absorption of energy. The lines are produced when the electrons go from higher to lower. So choice 1 and 2 only. So the answer there is A. Number 5, the values for the first 3 successive ionization energies for 2 elements X and Z are given. Which pair of elements must they be? So remember, you can tell which group number an element is in based on where there is the largest jump in ionization energy. So if the jump happens after losing 1 electron, it'd be in group 1. So if I look for element X here, we go from 520 to 7,300. That seems like a big jump to me. The next one is only a difference of about 4,000. I'm not going to do math. It's a smaller difference. So that means once this element loses that first electron, it has a noble gas electron configuration, which means it must be a group 1 element. So X must be lithium. Now, if we look at element Z, we go from 1090 to 2350 to 4610. I don't see any big jump there. That means this element could lose 3 electrons and still not have its noble gas electron configuration. Well, beryllium would have that after losing 2 since it's in group 2. So the answer is B, lithium and carbon. All right, which oxides produce an acidic solution? Please remember that aluminum and silicate oxides make amphoteric solutions. So no. Ooh, we've got a non-metallic oxide there. Ooh, and a non-metallic oxide compound there. Remember, they're the ones that make the acidic solutions. It's the metallic oxides that make the basic solution. So the answer is C, 2 and 3 only. Which species will require the least energy for the removal of 1 electron? So this is all about ionization energy. Remember, you can remember the trend with the ice cream cone. Decreasing going down, increasing going across. So if I look, I want to eliminate some choices right away. So I already know it's going to take a buttload of energy to remove another electron from the sodium ion, because sodium is group 1. Once it loses 1, it has its noble gas electron configuration. Carbon is the same deal. Carbon has 4 valence electrons, so I'm going to go ahead and cross that one out. So if we look here, magnesium versus aluminum, well, if you look at the periodic table, we got aluminum, magnesium is to its left. So that's magnesium, that's aluminum, which means aluminum has a lower ionization energy, which means it'll take less energy to pull the electron from magnesium than it would from aluminum. Remember, aluminum has a smaller atomic radius, so even when it loses 2 electrons, its valence energy level is still closer to the nucleus than that of magnesium, which means it would take less energy to take the electron from magnesium. It's also why magnesium is more reactive than aluminum. All right, so number 8 says, what is correct for the complex ion in this? So remember, we're given the complex ion is what is in the square brackets. Now, this is bonded to the sulfate ion. You have to know that the sulfate ion is -2, which means the overall charge of that complex must be +2 because the complex itself is overall neutral. So we can automatically get rid of choice B and C. Now, when it comes to the oxidation state of iron, if the whole thing is 2+, we got to look at our ligands. Water is neutral. That's a chloride ion, which is not neutral. So then the question has to be, whatever we have to add to -1 to get +2 is what the charge of iron is here. So that would be +3. So it's choice D. Which species has the same molecular geometry as SO3 2-, the sulfite ion? Well, if I were you, I would go ahead and draw it to see. Because I know that with 3 atoms bonded to 1, it's either going to be planar or pyramidal, right? But I don't know off the top of my head about those 2 electrons. Now, so I want to check. Now, one thing I can tell you, the carbonate ion is planar. Carbon has 4 valence electrons and sulfur has 2, so something tells me it's going to be PF3, but let's see. So sulfur has 6 valence electrons. There's 3 oxygens. Each one has 6, so 18, and don't forget to add 2 for the additional charge. So that's 20 plus 6, 26 total electrons. I'm going to go ahead and put sulfur in the middle and connect to the 3 oxygen on the outside. I've got 2, 4, 6 electrons distributed so far, so I have to do 20 in total, starting with the oxygen. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, sweet. I've got an extra pair, which can go on sulfur. 3 bonds, 1 lone pair does mean trigonal pyramidal, which would be PF3. Remember, boron is our exception. BF3 would be that without the dots. SO3 without would be planar because we just have to take away those 2 electrons, which would give us the trigonal planar, and so is carbon dioxide. All right, so number 10 says, how many lone pairs and bonding pairs of electrons surround the central chlorine in ClF2+? It tells you chlorine is in the middle. So when you draw this, just go ahead and put your chlorine in the middle and do your fluorines. I almost said C because I'm so used to putting carbon in the middle. So again, we got to consider the valence electrons. Chlorine and fluorine both have 7. There's 2 fluorines, so that gives us 21 total, but that positive charge indicates 1 was missing. So we should have 20 total electrons in our structure. I've got 4 distributed so far, going up to 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Bangarang. Now, when you check, you should have the correct number of elements and the correct number of electrons. So that means there's 2 bonding pairs and 2 lone pairs. So the answer is D. Which compound has the highest boiling point? If you're asked about boiling, melting points, it's about intermolecular forces. Remember, the one that has that's either going to be ionic or has hydrogen bonding will have the highest. So there we have the aldehyde, dipole-dipole. Here we have the halogenoalkane, also dipole-dipole. There is F and H, but the F is bonded to the carbon, not the hydrogen. This is actually propanone is very slightly polar, but we don't have any, that oxygen, is bonded to the carbons, not the H. But here we have our amine. Amines have nitrogen bonded to hydrogen, which means we have hydrogen bonding, which is the strongest intermolecular force for molecular compounds. What is the number of sigma and pi bonds in this molecule? All right, so, check out this symmetry. We got a carbon-carbon double bond in the middle, and each of those carbons is bonded to 2 cyano groups. So remember, the cyano group is a triple bonded carbon to nitrogen. Okay. Now remember, sigma bond is always the first bond that forms between 2 elements. The other bonds are pi. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. So B and C are out already. Excuse me. And then for the pi, we've got 2, 4, 5, 7, 9. So we've got 9 and 9. So the answer is A. What is the hybridization of the circled carbon, oxygen, and nitrogen atoms? So the one thing these guys left off here are the lone pairs on these. All right, so nitrogen's got 1 lone pair, oxygen's got 2. Hybridization is from the number of domains. So 1, 2, 3 means that oxygen is sp2. So A and C are out. Now carbon is bonded to the nitrogen and the hydrogen. That's 4 domains total. So that would be sp3 for carbon, which tells us that it's choice D. And nitrogen would also be sp2 because you got 1, 2, 3 domains. So D matches. Number 14, consider the following reactions. I can already tell this is going to be Hess's law, right? When I do these, I like to label the delta H's as A, B, and C. And then to figure out what we're going to do to these, we have to look at our overall equation, find reactants in our steps, and manipulate the steps to make it match. And then we manipulate delta H. So the first thing I see here is iron 3 oxide. I have 1 mole of it on the reactant side. Hey, there's iron 3 oxide. In the step, there's also 1 mole on the reactant side. So when we're calculating delta H, we're just going to leave A as it is. And then we're going to add it to some form of B. Well, let's see. So the next thing I see is carbon monoxide. I see carbon monoxide in both steps. Yikes. So I'm going to skip it. Let's go to iron. So here I see, there's iron in the second equation. But in the overall, there's 2 moles of it on the product side. Over here, there's 1 mole of it on the reactant side. So the thing I'm going to add to A is going to be 2 times the negated value for B. So A is -3 plus 2 times the negated value for B, so 2 times -11, which is -3 minus 22 essentially, which would be -25. So the answer is A. Number 15 says, what is correct when barium hydroxide reacts with ammonium chloride? Well, the key piece of information here is that delta H for this is positive, right? So whether you're mixing the solids, but there's obviously water here because you're making aqueous, right? And water. So the temperature will decrease because the reaction sucks thermal energy from the surroundings. So the temperature of the surroundings will decrease. Now, if it's endothermic, that means something's gaining energy. The more energy it has, the less stable it is. So products will have lower enthalpy. No, enthalpy's been gained the whole time. So the products will have higher enthalpy and they're less stable. So C is the correct answer. I worked through this paper earlier. I got 3 wrong. All the ones I got that one wrong. All the ones that I got wrong were because I rushed and I didn't think my way through things. But of course, when you take your test, once you answer everything, go back and double check just in case. All right, so 16 says, what are the signs of delta H and delta S for the reaction when it's spontaneous at low temperature and non-spontaneous at high temperature? So remember, we gotta be going with the drives of the universe. So the drives of the universe are delta H negative and delta S positive, but we're not always spontaneous here, just spontaneous at low temperature. So the easiest way to remember, if it's only spontaneous at low temperature, is negative and negative. But let's think of a process that's only spontaneous at low temperature, and that would be a liquid freezing, right? Well, if you freeze, you go from liquid to solid, which represents a decrease in entropy, right? And freezing is an exothermic process, so that means delta H is negative as well. All right, so number 17, which change is exothermic? So A goes from a mole of chlorine molecules, or half a mole, excuse me, to 1 mole of chlorine atoms. That's the enthalpy of atomization, essentially breaking bonds. It's also the bond enthalpy, which is an endothermic process. Here is ionization energy. It takes energy to remove an electron. This here is lattice enthalpy. It takes energy to break that ionic lattice. So no. This represents electron affinity, which among those is the only negative enthalpy change. In other words, when I say among those, the ones we use for the Born-Haber cycles. 18 says samples of sodium carbonate powder were reacted with separate samples of excess hydrochloric acid. I guarantee they're not telling us that just for fun. All right, so we have our equation here, and it says reaction 1, we took 1 gram of this substance and added it to 0.5 molar HCl. And in reaction 2, we took the same mass and added it to 2 molar. Well, higher concentration means higher rate, but since we use the same amount of the limiting reactant, that means we're going to form the same mass of product. So B is the answer, but let's look at the other choices. The same initial rate? No, reaction 2 will have a faster initial rate because it's got a higher concentration. Total reaction time? No, the reaction time will be less. Choose me in reaction 2 because the faster rate. At the average rate? No. Because average rate would be the total thing, blah, 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 blah. But since that's smaller time, the answer is B. All right, moving right along. Number 19, what decreases the activation energy? There's only one thing, adding catalyst. Increasing temperature will mean more reactant particles can satisfy that activation energy because they're moving faster, they collide faster, right? Adding more reactants, well, if that increases the concentration, sure, that might throw the system off equilibrium, but it's going to re-establish. And then increasing collision frequency, not so much. That just means you're going to have more that satisfy it. But the only thing that lowers it is the catalyst. Number 20 says compound X and Y were mixed and the time taken for the color to appear was recorded at various reactant concentrations. All right, so this is initial rate method. To determine the order with respect to each, we got to look at one column where things stay the same and look at what happens to the other column. Just so you know, I got this one wrong too. I didn't get it wrong because I don't know the chemistry. I just assumed that this meant rate. So I said, oh, as you double, rate halves. I was like, that doesn't make any sense. But I was like, whatever, and I kept going, but it's time. So if I want to figure out the respect, and believe you me, there was a choice that I chose, which actually was by error, right? So that was what we call the distractor. So let's go ahead and determine the order with respect to X. So I'm going to use the first two rows here because the concentration of Y remains constant. As I double the concentration, the reaction time halves. So we doubled the rate. Doubling concentration, double the rate, means it's first order with respect to X. Well, riddle me this. Everything's gone. But let's just look at Y just in case. So for Y, I'm going to look at the first and third rows. As concentration doubles, the reaction time goes down by a fourth. So that would be second order for that. Yay. Number 21 says the rate expression for this reaction is, which is not consistent with the rate expression. So remember, the rate expression is the rate law, and it all comes from each step. Remember, if the slow step is the first step in the process or the only step, then the order with respect to each reactant is the coefficient for that reactant. But if the second step is the slow step, we have to look to see if an intermediate produced in the first step is part of our rate determining step. If it is, the reactants that went to making it do influence the rate of reaction. So A has the fast step first, but since those 2 moles of NO make our N2O2 intermediate, it'd be 2NO, 1O2, which matches. B is easy because there's only one step. So 2NO, remember, if it's the slow step is first, the coefficients are the order. So it'd be second order for NO, first order for oxygen, so that matches. If I look at choice C, the slow step is the first step. So this would give us NO to the first order and oxygen to the first order, which does not match. So goodbye you. For this one, again, slow step is the second step, but we got 1 NO in the first step, 1 NO in the second, and O2 in the first. So that would also be consistent. All right, 22. It gives you the value of the equilibrium constant, more light, at different temperatures. So what I see here, as temperature increases, so does the value for K. So remember, we can only change the value of K if we change temperature, and if increasing temperature increases K, that means increasing temperature pushes it toward the product side of the equation, meaning the forward reaction is favored, concentration of products increases, concentration of reactants decreases, and so forth. So which statement is correct? At higher temperatures, the forward reaction is favored. The rate of the reverse is greater than the rate of the forward. No, it would be opposite. Opposite, opposite. Concentration of both increase. No, one goes up, the other goes down. Which combination describes a system at equilibrium? So this is just memorize. You got to remember that the entropy is max and the Gibbs free energy is min. This for me is easy to remember because it's opposite what we typically like. Typically, the universe prefers low entropy, exothermic, right? So negative entropy, so it's opposite. So that's how I remember it. All right, so which two species act as Bronsted-Lowry acids? Remember, a Bronsted-Lowry acid gives up a proton in the reaction. So I just got to look at each thing. So H2PO4 going over to HPO4, that gave up a proton, so that's an acid. This makes hydroxide the base because the hydroxide gains an H, right? Gains a proton to become water, which must make water over here the other acid. So the answer is D, because water loses a proton to make OH minus. All right, what is the order of increasing pH? So increasing pH means low to high. So it goes from acidic, most acidic to neutral to most basic. So let's just go ahead and define each of these things. Sodium chloride, cation from strong base, anion from weak acid. So we got a neutral salt. So automatically I know that sodium chloride has to go in the middle. So at least choice A is out for now. NH4Cl, we've got the ammonium chloride. We have the cation from a weak acid, or weak base, anion from a strong acid. So that'll be basic. For the sodium ethanoate, strong base, weak acid, so it'll also be basic. And to be perfectly frank, unless we have pKb values, we really don't know the relative strength of these two things. So something tells me that there'll be another thing that tells us. And finally, oh wait, I'm sorry. Ammonium chloride is acidic because of that. I'm sorry. And then finally, sodium carbonate, strong base, weak acid. So that's basic. So automatically we know that we can't start with either of the basic things. So C becomes the default choice. We got acid, neutral. I guess we know now that sodium ethanoate would be less basic than sodium carbonate. Which species is not a Lewis base? Remember, Lewis bases have to donate a pair of electrons. Hydroxide ion has 3. The oxygen in water has 2. The P has 1. Ammonium does not. Yay. I'm trying to go quicker because we're already up to 25 minutes. Okay. So an indicator, HIN, has a pKa of 5.1. That means that this indicator changes colors somewhere between a pH of 6 and 7. All right, now remember, a indicator, since it has the pK of 5.1, it is a that means if it's going to show neutrality, the endpoint at a slightly acidic pH, that means we probably have the titration of a weak base with a strong acid or something like that. So remember, if we add acid, we're adding H+, right? So color B would be shown in a base, and if we add acid, it pushes it. Remember, if you add base over here, it pushes that way. So at pH 7, color B would be observed. Yes, indeed, because neutrality here is going to be right around 5, slightly acidic. That represents neutral for that solution. All right, so if the pH is higher than that, that means it would be basic. At pH 3, color B would be observed. No, because if we're at pH 3, it means we're adding acid, which would push it over to color A. At pH 7, those two things are equal. That is only true at the half equivalence point if you're titrating it. And at pH of 3, this side, there'd be less of that than that. That's not true because it's opposite. All right, which is correct for this reaction. So we need to know oxidizing and reducing agent. Just looking at this really quickly, I can tell you that the answer is D. And the reason why is because unless you're forming elemental oxygen and hydrogen, or you're forming a peroxide compound, the oxidation state of O and H will stay the same. But let's just see. Phosphorus goes here from 0. This is an elemental form over here to -3. So phosphorus is reduced to form that, which means it is the oxidizing agent. But if we look over here, we got -4 from oxygen, +2 from the hydrogen. So if this thing is 1 minus total, what are we going to add to get that 1 minus? So we got to add +3. So phosphorus is oxidized to form that. So indeed D. All right, 29, which describes the flow of electrons in a voltaic cell. Remember, they go from anode to cathode through the external circuit. Ions move from oxidizing to reducing in the salt bridge, right? Anode is negative, so the electron, so the anions flow into the oxidizing, but anyways, it's all about the movement of electrons in the external circuit. Which is correct for a redox reaction where the standard electrode potential is negative. Well, you should know that if the electrode potential is negative, that means delta G is positive, because if you plug in a negative E there, you get a positive delta G. So A and B are out. And for the K less than 1, K greater than 1, remember the natural log of a number less than 1 is negative. So negative times negative makes positive. So C must be the answer here. 31, consider these electrode potentials. What's the cell potential? Remember, the overall potential for a cell is going to be the reduction potential minus the oxidation potential, or you could take the oxidation and reverse it. So you see chromium goes from elemental to ion, so chromium is oxidized, which makes sense because the E value is more negative. So it's just going to be 0.85, 0.85 minus 0.74, which equals positive 1.59. I'm going to just go for 1 second here. I'm going to finish making this video, even though class started. All right, real quick, because the class is starting, I'm going to fly. I mean, 3 out of every 4 kids are going to be late anyways, but still. Which compounds cause the color of acidified potassium manganate 7 solution to change from purple to colorless? That means which alcohol could be oxidized? Primary and secondary, yes. Tertiary, no. So there we got our primary. There we got our secondary. Now, if you look at this one, you may be tempted to think it's tertiary, but this hydroxyl group is bonded to that carbon. It is bonded to 1, so it's also primary. So D, all will change the color. What's correct for benzene? Readily undergoes addition. Nope, it does electrophilic substitution. It contains alternate single and double carbon bonds and it is planar. You may think that, but it's got resonance. Its NMR spectrum shows 6 signals. Nope, those are equivalent hydrogen, so it shows 1 signal, and it will form a single C6H5Br isomer. I don't know what that means, but whatever. Well, I mean, I do if you react it with HBr or just Br. Oh yeah, because electrophilic substitution, so you'd make HBr and the bromobenzene. All right, which compounds react to form EAP? All right, so remember the bit in front is from the alcohol, the bit in the back is from the acid, so we got 4 carbons, so it's butanoic acid, so A and B are outski. And if that carbon that's bonded to H and the 2 methyl groups, that would be propan 2-all. Yes, you can come in. All right, number 35, I'm just making a video, almost done. Which statement about the reaction of a hydroxide ion with organic reagent is correct? All right, so 1-bromopentane is primary, so no, it's SN2. That's tertiary, which means it's SN1. Reaction with 1-bromopentane occurs slower rate than 1-chloropentane. No, because bromine has less electronegativity than chlorine, so bromine is a better leaving group. So the reaction with 1-bromopentane is slower than this. Well, that would be SN2, that would be SN1. SN1 is always faster, so D. Hey kids, I got 4 questions to answer. If you could try to keep it down for a second. 6, what's the major product of HBr with but1ene? So that's going to make some brominated isomer of butane, but it'll be 2-bromobutane because the secondary carbocation that would form is more stable than the primary one. How many chiral carbon? Can you come back in just a minute? I'm doing 3 questions to do. You kind of hovering over me is distracting me. How many chiral carbon atoms are present in one molecule? This, best thing you can do is draw it out. So we got that carbon there, which is attached to a pair of methyl groups and a hydrogen. Right? And it's bonded to a carbon that's bonded to hydrogen and chlorine, which is bonded to a carbon that's hydrogen and bromine, which is bonded to a methyl group. So remember, in order to be chiral, the carbon has to be bonded to 4 identical atoms or groups of atoms. Not that one because it's 2 methyl groups. This carbon's got the hydrogen, that mess, and that mess. So yes, this one has the hydrogen, bromine, that mess, and that one's 3 hydrogen, so there's 2. Well, that depends on you guys. I'm gotta finish making the video. What's the... Sorry. Yeah, it's fine. Yeah. Dev's in the back. He's right in the back of the blue shirt. I'm making a video. Hey, I was wrong. I got about a third of the class here with 2 minutes to the bell. All right, everybody leave me alone just for a minute. I want to finish what I'm doing. Don't approach the bench. Leave me alone for 2 minutes. Jesus. What's the ratio of areas under each signal in the proton NMR of 2-methylbutane? Helps to draw it out. All right, so all same environment, that hydrogen. So 4 environments. That one's already out. I got 6 in that one, so I get rid of the one with 6. 6, 1, 2, 3. Boom. Look at the board. Phones in the jail. Laptops closed. Go, come on, I'm trying to do something. I got 2 questions to go.
I'm leaving at 12, so I need my phone so that I can see when my mom texts me.
All right. I'm doing 2 questions. Leave me alone. All right, what are the absolute percent and percent uncertainties for the change in mass? You're given a final and initial mass. All right, so I'm not gonna yell at him. I'm yelling him enough. I yell at him enough. Remember, so to get the change in mass, we gotta subtract. Well, we subtract, we add the absolute uncertainties. So the absolute uncertainty will be 0.1. And then to get the percent uncertainty, it's gonna be the uncertainty under the measurement. The difference there is 20, so 0.1 over 20. No calculator, but 1 over 20 is 5%. So 0.1 over 20 would be 0.05%. So, or 0.5%. B. Finally, which technique? Bond lengths, bond angles, X-ray crystallography. There you go, kids.